All right, well, good morning and happy Wednesday. We'll I don't know what's going on here. We'll take a look. So on Monday, we introduced this concept of a Markov chain. Said we can eventually use it to generate values from a distribution that we want. In Monday, it was just we just said it's a stochastic process. And we just said it's going to just generate a sequence of values. These are random values that are related to the previous value, right? We say it's got the Markov property, meaning the next random value that we get depends only on our current state. It doesn't depend on the history of what's come before. Just kind of like where you are now is going to determine the next value. But the next value is going to be random. Markov chains do have something known as a limiting distribution, or they can. Not every Markov chain has a limiting distribution, but some of them do have limiting distributions. And the idea of a limiting distribution is if you let this Markov chain run forever, if you keep generating these random values, can we say something about the future random values? Much in the same way that when you flip a coin, even though you can't predict the next value, we can say in the long run, we should get 50% heads, 50% tails. So we have an expected distribution of outcomes despite the actual sequence of values themselves being random. Similarly, we have a Markov chain, and we say the values that are going to be generated are random, but they're unlike the coin flips. They're not IID. The next value depends on the previous value, but still, can we say something about the overall distribution of values? That's kind of what we want to do. So we showed you this example of a two-state Markov chain on Monday, and here we have two states, and I think I said it was like sunny or rainy or whatever, but here we're going to just have state 0 and state 1, and the probabilities of transitioning from one state to another are given by this transition probability matrix. And we said all the values have to be non-negative, and then the rows have to add up to 1. And that's what we see. Probability of going from 0 back to 0 is 0.8, but you can transition from 0 to 1 with a probability of 0.2. The probability of going from 1 to 1 is 0.4, but you can transition from 1 to 0 with a probability of 0.6. Okay? So, let's just kind of see as an example what would happen if I start the chain at state 0. Okay? And here is like a little visualization here. And so this is that probability, transition probability matrix, 0.8, 0.2, 0.6, 0.4, and we have state A and state B, and we can see when you're at state A, it often goes back to state A with a probability of 80%. When you sometimes it goes from state A to state B, that happens with a probability of around 20%. When you're at state B, you return to state A with 60% probability. You remain at state B with a 40% probability. Let's see. Let's see if it goes from B back to B. So it kind of gets stuck at A. Here it goes. Goes to B, goes back to, it seems like every time it goes to B, it wants to come back to A, but there's a 40% probability that it goes from B back to B. And anyway, we're just kind of gonna, there we go, generate a sequence of values, okay? So, that's A, and then B, and then A, and if we just kind of let this run for a long time, overall, what is the distribution of A's and B's? Okay, can we come up with that? So that's the idea that we want to get at. Now, how do I get out of here? So here I can just kind of just run the Markov chain myself. So I've got this probability matrix. I'm going to say I'm going to generate 100,000 values. We're going to start off at state 0. Okay, I'm going to have 0 and then I guess 99,999 NAs. And then I'm going to set a seed, but you know, you can set it to whatever you want. And then we're going to say for I in 2 through n. So from 2 through 100,000, so basically step 1, because we're starting, or at the next step, because the first value is at 0, what we're going to take is we're going to take the previous value. So we're going to take x at the previous one, which is either going to be a 0 or a 1. And I'm going to say that's going to correspond to row 1 or 2. Because remember, my states are either a 0 or a 1. Okay, so if I have state 0, so we look at the previous value, it's a 0. So then my row is going to be 0 plus 1. If my previous value was a 1, then my row is going to be 2. And then what I'm going to do is I'm going to draw a value, 0 or 1, using sample. Okay, I just want one value from 0 or 1. But the probability of 0 or 1 is going to come from the row. So if the row was 0, we're going to use 0.8, 0.2. And if the row was 1, we're going to use 0.6. If the row is 2, we're going to use 0.6, 0.4. So if the previous state was 0, then the row is going to be 1, and we're going to use 0.8, 0.2. If the previous row is x equal to 1, we're going to use row 2, and we'll use 0.6, 0.4. And that's going to determine our next value, x at time I. And then we go to the next iteration, and we keep going and going and going. So this will generate a sequence of values for our Markov chain. We can kind of take a look at the values themselves, but we can, at the end, we can just say, hey, what proportion, after running it 100,000 times, what proportion of the steps are in state 0? And I get 0.7497. What proportion of the steps are in state 1? Around 25%. Okay. And you know, we could see if we want to see the actual sequence. So I could run this. It takes about a moment to run, and I can just say, hey, let's look at like the first 100 values. Okay, and so remember. When it is at 0, there's an 80% probability that it stays at 0 and a 20% probability that it goes to 1. And when it's a 1, 40% probability it stays at 1 and a 60% probability it goes back to 0. So going from 1 to 0, here I went back to 1, and then here it kind of got stuck at 0 for a while. Then it went to 1, back to 0, 1, back to 0. Again, got stuck at 0 for a little while. 1, 0, it did a few 1s. Some 0s, some 1s, a whole bunch of 0s, okay? And then so sometimes we get these long stretches where there's a bunch of 0s, sometimes a few 1s, and so on and so forth. And the question is, in the long run, what proportion are 0s and what proportion are 1s? And so if in one instance, I let it run for 100,000 iterations, and we got around 75% zeros, 25% ones-ish, okay? Here, this time, I'm going to start my sequence at 1, okay? I'm going to have it run for 100,000. We're going to start at sequence 1, and we're going to do the same thing, okay? Look at the previous value. The row I'm going to use is going to be whatever number it is, plus 1. Okay, we're going to use the second row, and then we're going to select either a 0 or 1 from there. And then that's going to be the value. So I let that run for 100,000 times, and then I get something similar, around 75% zeros, around 25% ones. A little bit, proportions are a little bit different. Back, this slide it was 0.7497. Here it's 0.74685. And you know, we could try different seeds, and we can kind of see like what proportion of values do I get. Okay, so I could say, you know, what's the proportion here? That was with set seed 1. Okay, let me just try set seed 10. And then we can ask, okay, what proportion? So around 75% again, okay? And then just set seed 110, let it run. What proportion are 0? So, you know, after running with different seeds, it does seem to hover around 0.75, something around there, 0.7497, 0.7512, 0.7517, okay? So what's, you know, when we do it, you know, both simulations end up with approximately 75% in state 0, 25% in state 1, okay? And so this kind of hints at what our kind of long run frequency is. So even though we don't have independent, it's not a sequence of independent values, okay? They're random values and they depend on our current state. The next value depends on our current state. It does seem that in the long run, there is some kind of limiting distribution that we can get at, okay? And so we're gonna say, well, we'll use these symbols pi, and we'll say pi 0 is the long run relative frequency that the chain is at state 0. And for pi 1 will be the long run relative frequency that the chain is at state 1. And so we'll say there is some distribution, pi 0, pi 1, this would be kind of our limiting distribution that reflects the long run probabilities that the Markov chain or random values are 0 or 1. And so far, we might guess that pi 0 and pi 1 is something around 0.75, 0.25. That's just what it seems to be about, you know, after running some simulations here. Okay, but rather than just kind of saying like, well, this is what it looks like and this is what we're guessing, let's see if we can kind of figure this out mathematically a little bit, okay? So we're going to say, we'll kind of a little bit more formally define, and we'll say the fraction of time that our Markov chain spends in state j is going to be pi sub j. So if pi 0 is 0.75, and then that means the Markov chain is in state 0 about 75% of the time. And so the probability that random variable x at time n being some arbitrary time in the future, that unspecified time, is going to be in state j will be pi sub j. And what is going to be important to us is that it does not matter what our starting state is, okay? That if our initial value is 0 or initial value is 1, that if we let n go towards infinity, the probability that some value, random value x at some arbitrary time far into the future, the probability that it's 0 should be the same, whether the starting value is 0 or 1, okay? So it shouldn't matter if the first thing is a 0, first thing is a 1. In the long run, the probability of being at state 0 is going to be the same, pi 0, which in our case is going to be 0.75. Okay? So the distribution of the limiting distribution is independent of whatever our initial state is. Okay? Whether the first value is a 0 or 1 should not affect it. So this is how we're going to define the limiting distribution. We're going to say we have some distribution pi over some state space, okay? we have a very simple example with just two states, pi 0 and pi 1, but it could be, you can still have a limiting distribution over a much larger state space of the different states you can have. And we'll say, pi is the limiting distribution if you have some kind of Markov chain that, into the future, as n goes towards infinity, the probability that you're at state j, okay, is going to be pi sub j, regardless of what your initial state is. So whether pi 0 is 0, 1, 2, or n, so no matter where you are, in the long run, if the probability of being at state j is this, then that's going to be our limiting distribution. Okay. So if a limiting distribution does exist, okay, then that value pi sub j represents the probability that our random variable x at time n is in state j, independent of the initial state x0, and it also represents the long-run expected fraction of time that the Markov chain spends in state j. That's how we want to do it. Okay, so that's the limiting distribution. And a very kind of similar concept is what we call the stationary distribution. Okay, the stationary distribution is a distribution over states such that the expected distribution of the Markov chain at the next time is the same as the stationary distribution. Okay, so it's the distribution of kind of our system when it's at equilibrium, so that if we have this mix of 75-25% now, if our distribution is 75%, 25% now, at the next time, next step in time, okay, some are going to transition from 0 to 1, some will transition from 1 to 0, some will go from 0 to 0, some will go from 1 to 1, that everything's kind of at equilibrium, and that at the next time we'll also expect to be at 75-25%, or whatever our stationary distribution is. Okay, if there's kind of a flux, like currently, this side is too big and this side is too small, and at the next step it kind of changes, okay, then that's not at equilibrium. Okay, and so what we're going to say, if the limiting distribution of a Markov chain exists, that limiting distribution is the stationary distribution. Okay, and there's kind of this term we use, and we'll say if a Markov chain is ergodic, that means it will eventually converge to a stationary distribution. Okay, all right. So I'm gonna give you some kind of informal definitions for Markov chains. There's some more mathematically rigorous ones, but we'll just kind of go with some informal ones. I think a little easier for us. Okay. So we'll say a Markov chain is said to be ergodic if we can start the chain at any state I, so any state in this current state space, and then at some time in the future t, some arbitrary finite time in the future t, the probability of being in any of the other states is greater than 0. Okay, so basically we're saying if you start here, just given some arbitrary length of time, we can reach basically anywhere else. Okay, anywhere else. So kind of if you have like some states that are like islands, and you don't have that's not going to work out. Okay, but if even if it's a very low probability, as long as there is some probability of getting somewhere at some point in the future, then we'll say this is true, that it is ergodic. Now, so we're going to kind of break this down into two parts. One is that it's going to be irreducible. That's kind of the idea that you can get anywhere. And then there's this other part that says the Markov chain has to be aperiodic, and I'll explain that in just a moment as well. Okay, so irreducible is this idea that all of the states communicate with each other. Communicate's kind of a weird word, but that's the word that gets used. Basically, that you can connect, right? There's a way to get from state 0 to state 1, 2, 3, or 4. Okay, if you start off at 0, you can end up at state 4. You have to go through state 1, 2, and 3 first, but you can get to 4 eventually. Right? If you start off at state 3, you can get to any of the other states. You can go from 3 to 4 directly. You can go from 3 to 2. You can also get to 0. You have to go through 2, 1 first, but you can, if you start off at 3, there is a path for you to get to 0. Okay, so in this diagram, all of our states, okay, every pair of states, I and j, okay, is there is a path that exists. So we'll say all states I and j in this diagram communicate, and therefore this Markov chain is irreducible. All the states communicate with each other. If you start any of the states, there is a path to any of the other states. Okay. Whereas here's an example that is not irreducible, or this one would be reducible. Okay. All of the states do not communicate at each other. Okay. If you start at, say, 0, there is no way for you to get to 3. Okay, right? You can go from 0 to 1, 1 to 2, but when you're at 2, you really can only go back to 1. Okay, you can go back to 2, or you can go to 0, or whatever, but there's no way for you to go from 0 to 3 or 0 to 4. Right? So all of the states do not communicate with each other. If you start at any 0, 1, or 2, there's no path to get to the states 3 or 4, all right? And we call this a reducible chain, okay? Because, this is our state diagram. But we can say if you start at 0, 1, or 2, you can reduce the diagram just to those 3 states, okay? There's no point in keeping states 3 and 4 in your diagram for chains that start at 0, 1, or 2. So we could kind of reduce our diagram here, okay? So this would be reducible. This is irreducible. Irreducible, everything can get to any of the others. This one, not all of them communicate, okay? So that's kind of the concept of reducible versus irreducible. So if for us to have a Markov chain that's ergodic, and again, ergodic kind of means that it will eventually converge to a stationary distribution, okay? It has to be irreducible. All of the states must communicate with each other, okay? The other part is that the Markov chain has to be aperiodic, okay? Aperiodic. So what does it mean to be aperiodic? Well, first we have to introduce what the period of a Markov chain is. Okay, hang on, let me give you, oh. Okay, no, I got logged out. Here, let me get logged back in here. So the period of a state is our greatest common divisor of the number of steps that you can take and end up back at kind of the starting state. Okay, the period of a state. So let's say we look at state 3. What is this? Okay. So let's say we look at 3. Can we get back? How many steps does it take to get back to state 3? Okay, so I can go from 3 to 4. Back to 3, and that would take me 2 steps. Or I can go from 3 to 2, back to 3, and that would take me 2 steps. Okay? I can get back to 3 if I take 4 steps. I can go 3 to 2 to 1, back to 2 to 3. So, right, this is 1 step, 2 steps, 3 steps, 4 steps. Okay? Or I could take 6 steps. I could go 1 step, 2 steps, 3 steps, 4, 5, and 6. Okay, and so we list off how many times it takes, right? And even going like 1, 2, 3, 4, and ending up back at 3 this way, Okay, that's allowed. Okay, that says you can get back to yourself in 4 steps. So if you look at all of these things, we can get back to 3 in 2, 4, 6, 8, some even number. Okay, so we have a state period of 2. Okay, it is not possible to get back to the starting state in just 1 step. Okay, or 3 steps even, right? If I say, hey, take 3 steps, can you get back to 3? There's no way to end up back at 3 in 3 steps. Okay, it has to be some even number. Right? And so, and if you look at this, basically every state has a state period of 2. Okay, in that it takes some even number to get back to where you started. And so this would make a Markov chain, it would not have a limiting distribution, or it would not be ergodic, because if we started at state 3, I will know that if I'm in an even number of states from now, or even not number of states, even periods of time from now, then there is a non-zero probability of being back at 3. Okay, but if my n is an odd number of periods of time from now, then I have a 0 probability of being back at 3. Okay, and remember, where did I say? Okay, something is ergodic if the probability of being in any of the future states is greater than 0. Okay, so we have to have some non-zero, some positive value for being in the state. And if I say, well, I know at some odd time in the future, 0 probability of being at state 3, then it's not going to be ergodic. All right, I think I'm logged in now. Give me a second here. It is week 5, Wednesday. Do I have, I don't have it published, or do I have it published? Okay, let me publish the quiz. Is it published now? Okay, the first answer is B. B as in bear. B. Okay, so here's one. Very similar diagram, okay? But look what I have here. It is possible to go from state 4 back to state 4. So with that, I can get back to state 3 in 2, 3, 4, or 5 steps. I can go from 3 to 4. This is 1, 2 steps. I can get back to 3 in 2 steps. Okay. I can get back to 3 in 3 steps. 1 step, 2 steps, 3 steps. Okay. I can even, I can take 5 steps. I can go from 1, 2, 3, 4, and 5, right? I can repeat going to 4 over and over and over again, right? So once you have the ability to go from one state back to itself directly, then the whole chain becomes aperiodic, because, if you said, hey, I want you to go from state 0 back to itself in, just pick some arbitrary number, you say, 87 steps, you could do it. 88 steps, you could do it. 89 steps, you could do it. All you have to do is just keep repeatedly go from state 4 back to state 4 over and over again. Okay, even if this probability is very low, just the fact that you can do it makes it a non-zero probability. Okay, so here this thing is aperiodic. The greatest common divisor among all these number of steps, 2, 3, 4, 5, et cetera, is going to be 1. So this thing has a period of 1, and all of these states have a period of 1. Okay, so Markov chain is aperiodic if all the states have a period of 1. And basically, if you see in a Markov chain that one step can go back to itself, then the entire Markov chain will become aperiodic. So if a Markov chain is irreducible, meaning all of the states communicate, and at least one of the states can go back to itself, then the Markov chain will be aperiodic. All right, so here we have our two-state Markov chain, states 0 and 1. We can go from state 0 back to 0, state 1 back to 1, okay? And we can see, yeah, you know what? I can go from state 0 back to 0 in 1, 2, 3, 4, 5, some arbitrary number of things, so it's aperiodic, okay? We also see all of the states communicate to each other, okay? I mean, there's only two states, and it's possible to go from one to the other and the other to one. So this is also irreducible, and that means our chain is ergodic, and there will be a limiting distribution, which will be the stationary distribution, okay? And again, the stationary distribution is achieved when we achieve this equilibrium. That is the probability, the total probability of something transitioning from state 0 to state 1 is equal to the probability of transitioning from state 1 to state 0. So the transition probabilities are 0.6 and 0.2, but if kind of the amount flowing from 1 to 0 is equal to the amount flowing from 0 to 1, then we have achieved this equilibrium. So if you start at state 0, the probability of going to state 1 is 0.2. That's the probability of P01. Okay, P01 is the probability of starting at state 0 and going to state 1. That's 0.2. And the total probability of transitioning from state 0 to state 1 is going to be the probability of starting off at state 0 multiplied by that transition probability. So it's the probability of starting at state 0 multiplied by the probability of transitioning to state 1. So it's going to be P0 times that transition probability P01. Okay? And similarly, the amount flowing from 1 to 0 is going to be the probability of starting at state 1. Okay, so that's going to be P1 multiplied by the transition probability of going from 1 to 0, 0.6. So we're going to have whatever this thing is times 0.6, P10. And what we want to do is we want to set those things equal to each other, okay? So we want to find some values of pi 0 and pi 1, okay? So that when we start off at state 0, our stationary probability, pi 0, multiplied by the transition probability of 0.2, it's going to be the same as the amount kind of flowing in the other direction. Pi 1 is probability of starting off at state 1, multiplied by the transition probability of going from 1 to 0, which is 0.6. So we need 0.2 times pi 0 equal to 0.6 times pi 1. And we know that our stationary distribution, pi 0 and pi 1, have to add up to 1. Okay? So I have two equations, 0.2 pi 0 equal to 0.6 pi 1, and and this equation, pi 0 plus pi 1 equals 1. So I've got two equations, two unknowns, just a little bit of algebra, and we can solve. And so, just doing divide both sides by pi 1, you get pi 0 over pi 1. Divide both sides by 0.2, you get 0.6 over 0.2. You're going to get pi 0 over pi 1 is equal to 3. And then if you plug that back into here, okay, then, you'll get pi 0 equal to 3 pi 1, okay? And solving for that, you'll get pi 0 is equal to 0.75, and pi 1 is 0.25. Okay, so solving these two equations and two unknowns, you'll get 0.75 and 0.25. All right, and that explains, or that makes sense, because that's what we observed empirically when we just kind of ran the Markov chain for like 100,000 iterations. We saw it hovering around 75%, being in state 0. Okay. Just to kind of illustrate this, if you start off with your stationary distribution being 0.75 and 0.25, and you multiply it by the transition probability matrix, you'll see you get back your stationary distribution. Okay, so 0.75. So remember, this is the probability of being in state 0, and we can say, okay, what is the probability of ending up at state 0. Okay, so we would multiply this by the transition probability matrix, right? So this is 80% of those that start off in state 0, okay, 0.75 times 0.8 will end up back at state 0, okay? And then 60% of those in state 1 goes back to state 1. So we do 0.25 times 0.6, and that's going to be 0.15. So we get 0.6 plus 0.15, oops, and we can see that's going to add up to 0.75. If you are in state 1, okay, there is, or if you start off at state 0, okay, there's a 20% chance that you can flow to state 1. So 0.75 times 0.2 is 0.15. If you are in state 1, okay, which is 0.25, the probability that you'll remain in state 1 is 0.4. So the total probability of staying in state 1 is going to be 0.75 times 0.2 is 0.15 plus 0.1, okay, so 0.25. So we can see this is, we started off at 0.75, 0.25, and even after applying the transition probability matrix, we end up back at 0.75, 0.25. And we can kind of see this amount, 0.25 times 0.6, this is the amount flowing from state 0 to state 1, that's 0.15. And then this, this is the amount flowing from state 1 to state 0, 0.25 times 0.6, going from 1 to 0, probability of 0.25 starting at 1. And then this probability, 0.75 times 0.2, this is the amount flowing from 0 to 1. Okay, 75% probability of starting off at 0, 20% probability of flowing to 1. So 0.75 times 0.2 is also 0.1. So we can see this is 0.15, this is 0.15, and so the amount going from 1 to 0 and 0 to 1, those balance each other out. So that's our stationary distribution there. Okay. Let me see, there's this diagram. Let me see. Okay, so can't quite get it. All right, so this is supposed to be around, what did I say? Okay, so we want a 20% probability of going from one state to the other. So, I don't know. Okay, there we go. And then we want a 60% probability. There we go. Okay. So this is kind of a diagram kind of showing migration between California and New York, but you can think of it again as two states, state 0 and state 1, okay? I guess these are literal states in the United States. This represents kind of the transition probability. This is the transition probability that somebody from California moves to New York with a probability of 0.2, okay? And then this is 0.6 is the probability that someone goes from New York to California, 0.6, okay? Probability of going from New York back to New York is 0.4, probability of going from California back to California is 0.8. And so here is a little diagram, okay? And what we're gonna see is we're gonna see 20% of, this represents California, 20% is gonna go from here to here, and then here we're gonna have 60% from this go from here to here. And this has now achieved equilibrium where the amount flowing from here to here is equal to the amount flowing from here to here. I can restart it, and we start off with kind of different sizes, but eventually the amount flowing is the same. And you can kind of you can play around with this, and you can grow one to be much bigger and much smaller. Okay. So here I have nobody over here, and so when I restart, we're going to just see 20% going from here to here, and 60% of this circle going from here to here. So 20% and 60%. 20%, 60%. And eventually, we have equilibrium. The amount going from here to here is equal to the amount flowing back. Okay? And you can have everybody start over here. 60% is going to go from here to here. 20%, 60%, and it takes a little while, but not too long, and now we've achieved equilibrium again. Okay, you can kind of have this and this. 20%, 60%, and then eventually we achieve equilibrium, and that equilibrium is achieved when this is basically 75% and 25%. Okay. All right. So we did a little bit of arithmetic to solve this, but there's a way to kind of solve this naturally. All right. We have, if we think about this, the stationary distribution is this vector pi, right? And we have this transition probability matrix, capital P, right? And so we're in the form of vector times a matrix is equal to vector times scalar, the scalar being 1. Okay? And so this is in the form of, vector times matrix equals vector times scalar, which is an eigenvector. Okay? Traditionally, when you see an eigenvector, it's normally matrix times vector is equal to scalar times vector. But you can have it in the other form. We call this a left eigenvector. Okay? It's a left eigenvector if it's vector times a matrix, which is what we have. Okay? So normally, you have a right eigenvector, which is matrix times vector is scalar times vector. Here we have vector times matrix is equal to vector times scalar 1. So the left eigenvector, okay, is equal to the transpose of the right eigenvector of P transpose. So here I want to find the left eigenvector of P transpose. So I can transpose the entire thing, and I would get P transpose pi transpose, okay? And so this is now in the form of matrix vector. So if I take P transpose and I say that's my matrix, then pi transpose is our eigenvector, right eigenvector, okay? So we just basically find the right eigenvector of the matrix P transpose, and then we just transpose that. So that's easy, okay? So if this is my matrix P, I can ask R to calculate the eigenvectors of P transpose. So I can just say eigen of P transpose, and this will be my eigenvectors. And we're going to just take the first one, okay? The first column, these will be my things, and this will be the first column, and I've transposed it, okay? Now, one thing is that when R calculates eigenvectors, it's so that the, the norm is equal to 1. So 0.948 squared plus 0.316 squared add up to 1, okay? But what we want is we want everything to just kind of remain proportional. So I'm going to just take the sum of this 0.9486 and 0.3162. I'm going to take the sum of that and just scale it down, okay? And we can see that, oh yeah, this is, this value is 3 times greater than this value, right? And so when you scale everything and you say that everything has to add up to 1, we're going to get 0.75 and 0.25. So this is the stationary distribution, okay? So the stationary distribution is just this first column, but scaled down so everything adds up to 1. 0.9486 plus 0.3162. We're just going to take that first column from our eigenvectors, and then we're going to just divide by the sum of these two values so that it scales down to 1. Okay, so this is our limiting distribution. When you take the current distribution at time n, multiply it by the transition matrix. It will give you the probability of distribution at the next time, time n plus 1, okay? And if you continue multiplying by the current distribution, it will eventually converge to the stationary distribution, assuming that the chain is ergodic. Here, let me, before I forget. Second view quiz answer today is the letter D. D as in dog. D as in dog. So here's my transition probability matrix. We already know it has a stationary distribution, 0.75 and 0.25. But what I can show you is that if you start off with the distribution 1, 0, and you multiply by the transition probability matrix, at the next step, you're going to get 0.8, 0.2. If you take 0.8, 0.2 and multiply the transition probability matrix, you'll get 0.76, 0.24. Okay, 0.8 times 0.8 plus 0.2 times 0.6, 0.64 plus 0.12. And then if you take that, 0.76 and 0.24, and multiply the probability matrix, transition matrix, you'll get 0.752, 0.248. And if you keep running and running and running, okay, so here it is. I'm just doing it one step at a time. I'm just doing x times p, updating my x each time. Okay, after a bunch of iterations, it converges to 0.75 to 0.25. Okay, if I start off with the opposite distribution, everybody's at state 1, 0, 1. Okay, I multiply by the matrix, I get 0.6, 0.4, then I multiply by p again, 0.72, 0.28, multiply by p again, I get 0.744, 0.256. Keep going after a bunch of iterations, converges again, 0.75, 0.25. So you can keep running this over and over and over again. Some of you took Stats 102A with me, and one of my homework assignments was code up Monopoly and find the kind of the stationary distribution of Monopoly, like overall, if you just let the game run, where are you going to end up? And you did that by kind of coding up the rules. And you said, like, if you land here and you draw the chance card, then move here. And if you go here, then move, do this and do this and do that. You could also solve it using a Markov chain, okay, or a giant transition probability matrix. You would need all 40 squares, and you can say, all right, if you start at go, then the probability that you end up at this space, you take in the dice rolls, you take into account, like, okay, if you land on the jail space, then you end up over here. And it would be this really complicated matrix, but it could be done, and then you can let it run forever. Or you can just kind of say, where does it converge? And eventually you get that. And this is, I haven't checked these links in a while. But here are some papers where they took a Markov chain and a transition probability matrix approach to solving this Monopoly problem as well. Okay? All right, so what we saw today is that we can use a Markov chain and eventually reach a stationary distribution where we can just say, no matter where you start, if you let this Markov chain run long enough, eventually the values that it produces will follow a certain distribution. The values aren't IID, okay? So it's not like flipping a coin and in the long run it runs 50%, 50%. But we can still say, if we have some kind of transition diagram, eventually, if it's ergodic, eventually it'll reach some kind of stationary distribution, and maybe that stationary distribution we'll get values from that stationary distribution, okay? So the idea that we want to go to next is, can we design a Markov chain, okay? Can we figure out the transition probability matrix so that the stationary distribution reflects some desired distribution that we want, okay? Because again, the big picture is we want to be able to generate random values. And we said, well, maybe all of these other methods have failed us. So can we use Markov chains to create a stationary distribution that is going to be the desired target distribution? Okay, and so that's what we'll do next with the Metropolis algorithm. Okay, we'll end here, and let me give you your last view quiz answer.